Hello good people, I'm going to talk about valence electrons, valency and ions. You have already encountered valence electrons, but what fresh horrors are valency and ions? I'm going to look into valency first, and to that end I'm going to bring in another table. Recall that the valence electrons are the electrons in the outermost energy level, and that elements within the same group will have the same number of valence electrons. So all elements in group 1, for example lithium, will have 1 valence electron. All elements in group 2, for example beryllium, will have 2. All elements in group 13 will have 3. All elements in group 14 will have 4, and so on, all the way up until group 18, the noble gases, where we end up with 8 valence electrons. I'm going to write the number of valence electrons beneath the periodic table as well. Alright, so what is valency? It sounds awfully similar to valence electrons, but it is not the same thing. Valency, or the valence of the atom, refers to the number of electrons that are either donated or accepted by that atom. In other words, valency refers to the number of electrons that need to be lost or gained in order to end up with a stable electron configuration. A stable electron configuration is the electron configuration of a noble gas, the one where the outer s and p orbitals are complete. And there is a bit of a pattern for valency as well. All of the group 1 elements have a valency of 1. Group 2, valency of 2. Group 13, valency of 3. Group 14, valency of 4, and now we start going backwards. Group 15 have a valency of 3, Group 16 valency of 2, Group 17 valency of 1, and Group 18 noble gases have a valency of 0. The noble gases already have a stable electron configuration, so they do not need to lose or gain electrons. Fair enough. I'm going to add the valency values beneath my periodic table as well. Okay, but how do we know whether an element will donate or accept an electron? Well, it will depend on whether the element is a metal, non-metal, or a metalloid. Let me highlight those on the periodic table. Metals are highlighted in red, non-metals in blue, and the metalloids are yellow. It turns out that metals tend to donate electrons, while non-metals tend to accept electrons. This results in formation of ions. But before I look into ions, I want to talk a little bit about this word tend. What does that mean? Well, it means that metals are likely to donate electrons and non-metals are likely to accept electrons. But it does not always have to happen. For example, hydrogen is a non-metal, but in quite a lot of cases it is actually going to donate its electron. In other words, it is likely to behave as though it were just another metal in group 1. The situation is also not as clear-cut when it comes to the metalloids in yellow. For example, boron is likely to donate electrons, but then antimony and tellurium are likely to accept electrons. So once again, there are rules, but then there are also sub-rules. At this stage, we are focusing on the general main trends. And the general main trend tells us that metals will donate electrons, while non-metals will tend to accept electrons. All right, so let's look at what these ions are all about. Let me get rid of this, so that I can dazzle you with a whole new set of definitions. Firstly though, a bit of revision. Recall that atoms in their ground state have the same number of protons and electrons. In other words, the number of positively charged particles, protons, equals the number of negatively charged particles, electrons. This means that overall there is no charge. Atoms in their ground state are neutral. This is not the case for ions. An ion of a particular atom has the same number of protons as the atom, but a different number of electrons. In other words, the number of particles that carry a positive charge is not equal to the number of particles that carry a negative charge. Ions are not neutral. They will have a charge. For example, an atom of sodium has 11 protons and 11 electrons. An ion of sodium will still have 11 protons, but only 10 electrons. In other words, there are more positive charges than there are negative charges. When an ion contains more protons than electrons, it becomes positively charged and it is known as a cation. On the other hand, when an ion contains more electrons than protons, it becomes negatively charged and it is known as an anion. A more proper definition would be an atom that donates an electron becomes positively charged and it is known as a cation, while an atom that accepts an electron becomes negatively charged and is known as an anion. Notice, it's not an onion, it's an anion. Generally speaking, metals will become cations, and non-metals, with the exception of hydrogen, will become anions. They will end up gaining electrons. Fantastic. But at this stage you might be wondering, how will you know the charge of a particular ion? Here too, the periodic table offers a pattern. It turns out that all of the elements in group 1 will end up with a positive 1 charge. All of the elements in group 2 will end up with a positive 2 charge. All of the ones in group 13 will end up with a positive 3 charge. What about group 14? Well, I'm going to skip this one for now. Group 14 is a bit tricky. It has a valency of 4. So this means that 4 electrons will be either donated or accepted. Carbon, silicon, germanium and tin can either accept or donate 4 electrons. Lead, on the other hand, is most likely going to donate 4 electrons. So once again, group 14, a little bit tricky. And for now, we are not going to worry about it too much. So let's go to group 15. What happens there? Well, now we are firmly in the non-metal territory. And the non-metals will accept electrons. The valency of group 15 is 3. So it's telling me they will accept 3 electrons. As a result, they will have more negative charges. More precisely, they will have 3 more negative charges, and therefore they will have a negative 3 charge. Group 16 will have a negative 2 charge, group 17 will have a negative 1 charge, and group 18 will not accept or donate electrons, therefore it will remain neutral and have a 0 charge. Okay, so now beneath my periodic table I have 3 sets of numbers. Valence electrons, valency, and the charge. The story of these numbers is connected, but they do not tell the same thing. Valence electrons are the electrons in the outermost energy level. Valency tells me how many electrons are either donated or accepted. And the charge tells me something about the charge on the ion that will result once an atom has either lost or gained electrons. Okay, now let's look at a few examples and how we might represent this using chemical symbols. So here we have a lithium atom. It is in its ground state. It is neutral. It has 3 protons, 3 electrons, and a charge of 0. Lithium is a metal. It is likely to donate an electron. How do I represent this using chemical symbols? Well, I'm going to use a reaction arrow. So this is telling me that I will start with lithium and then end up with something else. As I said before, lithium is a metal, so it is likely to donate electrons. How many electrons will it donate? Well, according to the valency, it will donate 1 electron. So I'm going to end up with a free floating electron, and I will end up with a lithium ion. But I need to indicate the charge of this ion. What will be the charge? Well, let's analyze the situation. It is still a lithium, so it still has 3 protons. but it has lost an electron. So now it has 2 electrons. This means that it has 3 positive charges and 2 negative charges. So overall, it is 1 positive. And the way we indicate that here in our symbol is by placing a plus in the upper right corner. So on the left, I have a lithium atom. On the right, I have a lithium cation. Let's do the same thing for calcium. So I'm going to start with a calcium atom, and then I will end up with something else. Initially, calcium is neutral. It has 20 protons and 20 electrons. So the overall charge is 0. Calcium is a metal, so it's going to donate electrons. How many? Well, according to the valency, 2. So I will end up with 2 free-floating electrons, and I will end up with a calcium ion. What will be the charge? Well, again, I can analyze the situation. It is a calcium, so I still have 20 protons, but I have lost 2 electrons. So I only have 18 electrons. This means that my charge will be plus 2. I have 2 more positive particles than negative particles. How do I indicate that on the chemical symbol? Well, in the upper right corner, I will write 2 plus. I have started with a calcium atom that has lost 2 electrons, and I have ended up with a calcium cation. At this stage, you might be wondering what is happening with these free-floating electrons. Well, we will talk about them later on. For now, think of them simply as footloose and fancy-free. Maybe they've gone to the library. So these were examples of cation formation. What about anion formation? Well, let's look at a few of those. So I'm going to look at fluorine. And we are going to do the same analysis with regards to number of protons, electrons, and the charge. A fluorine has 9 protons and 9 electrons. It is neutral, therefore the charge is 0. A fluorine is a non-metal, so it is very likely to accept electrons. How many electrons will it accept? Well, according to valency, it will accept 1 electron. So I'm going to say I have a fluorine atom, and it will accept a single electron. And that will give me a fluorine anion. What is the charge? I still have 9 protons, but now I have an extra electron. I have 10 electrons, which means that the overall charge is -1. And so up here on the symbol in the upper right corner, I will write a minus. So I have started with a fluorine atom that has gained an electron, and I have ended up with a fluorine anion. Let's look at one more. I'm going to pick sulfur. So sulfur has 16 protons, 16 electrons, and is therefore neutral. It has a charge of 0. Sulfur is a non-metal. It will accept electrons. How many? Well, according to the valency, it will accept 2 electrons. So I'm going to write sulfur plus 2 electrons. And that will give me a sulfur anion. What will be the charge? Well, I still have 16 protons, but now I have 2 extra electrons. There are 18 of them, which means the charge is -2. And the way to represent that on my chemical symbol is to write a 2 minus in the upper right corner. Here too, you might be wondering, well, where do these free electrons come from? It is a good question, and we will talk about it in later videos. Right now, you need to get comfortable with the concepts of valence electrons, valency, and ions. Metals will tend to donate electrons and become positively charged cations, whereas nonmetals will tend to accept electrons and become negatively charged anions. This story does not end here, but before you start questioning my heritage, I'm going to say that is all for now, and I will see you on the flip side.